Okay, morning, guys. Today I'm not going to finish this whole 7.2 up today. I'm going to try to keep this relatively short. Go through 1, 2, 3, 4, 5. I'm going to go through 5 examples, okay, and then I'm going to finish up the last 2 in that old AP problem on Monday, and hopefully we're going to knock that out in about 20 minutes. And then there's going to be a formative for the remainder of the class on Monday for you to do. So hopefully you're listening to this video to know for sure that there will be a formative on Monday. Okay, so what we're doing is we're finding the area of the region enclosed by y equals 2 minus x squared and y equals 2 cosine 2x. So you can graph these. I know you'd be capable of graphing these. They would probably give us the graph on this one. And if they gave us the graph on this one, okay, it's going to look like this, except if it were me, I would want to zoom in on this graph a little bit, okay? Like I would make my window to see where they're intersecting here. I'm probably going to take my window -3 to 3 for the x's and probably -3 to 3 for my y's. So I'm going to quickly grab here and I'm going to do my window zoom, change my window settings. I'm going to go -3 to 3, scale of 1, -3 to 3, and give myself a scale of 1, and I'm going to hit enter just so I see a nicer area here, and I can see the area bounded between these curves, okay? They're like little dog ears here. And if you can picture in your mind to find these limits of integration, it's going to be another one of those no thank yous, because we're going to be looking, when is 2 minus x squared equal to 2 cosine 2x, and it's really no thank you to find that, so that's why we're graphing this in our calculator. And I'm going to have the calculator find my limits of integration, and there's a fast, easy, short way to do this. I can do, because see, there's actually 3 intersection points here, and I could do this 3 different ways by going menu, analyze graph, and do intersection, but I'm kind of lazy. Everybody knows that about me, so I'm going to go menu, I'm going to go geometry, points and lines, intersection points, and then you select the 2 graphs you want to intersect, and it grabs the intersection points for you, and it labels them for you right away. And then I got, oh, come on, baby, come on. Uh-oh, escape, and I want that. I want to grab that guy. There we go, I got that one up there. So then, because I can do this and I can cheat, I'm going to take tools and I'm just going to capture that page, and I'm going to come back and I'm just going to paste that little bugger here, okay? And you're just working this in your calculator, and hopefully you graph this, because a big part of this test is being able to adequately use your technology to find these areas, okay? And if this were on there, typically the AP board is going to say, show the integral setup that leads to your answer. And so we're basically, not basically, we're looking for this area bounded between the curves, and they're kind of these little dog ears that I got going on. And I know the cosine is symmetrical about the y-axis, so it's an even function. I know this parabola, because the vertex is on the y-axis, is symmetrical, so I have 2 even functions. So I actually have 2 ways I can do this. Okay? I have multiple ways I could do this, actually. The fastest, easiest way is I'm going to look at the integral from my a, which is negative 1.895 to my other limit, 1.895 of my function. Now notice, when I draw my rectangles in here, no matter where I draw my rectangles, my heights are always on there. That second one's pretty bad. But remember, it's going to be my upper curve, which the blue one is on top, so I'm going to be 2 minus x squared minus my other one is going to be 2 cosine 2x, and then I'm going to call that dx, just to give it a rainbow of colors. Okay, that's one way to do that. I can type that straight into my calculator. Or if I want to use symmetry, notice if I find the area of one of these ears are symmetrical. So it would also lead to, say, 2 times the integral from 0 to 1.895 of my 2 minus x squared minus 2 cosine 2x dx. And yes, I am kind of a parenthesis nut, but that's just the way I was. And then from here, these are the integrals. I could use this one, or I could use this one, okay? And then also remember, if the AP board said f of x actually equals 2 minus x squared, and that's my blue function, and they defined this one as g of x equaling 2 cosine 2x, okay, if they define my functions as f and g, I don't have to write it out like this, just so you know. I could use either one of these integrals, and I could say the integral 2 times from 0 to 1.895. And what I'm doing is my blue one, I'm taking f of x minus g of x dx. If the AP board defined your functions like that, this integral setup would work as well, okay? And we're not going to longhand this one out because I don't want to, and I want to keep it short. So you could go to the calculator page and you could do that, or hopefully what we're going to do here is we're actually going to come here and we're going to find the bounded area, okay? So, you know, the AP board knows that these capabilities are inside here. I'm going to analyze graph, and I don't want integral. I'm going to do bounded area, and my lower bound is going to be this point, right? Well, I need my, hold on, I got to go backwards. I can't do that with my finger. So I'm going to come over here, and I'm going to say menu, analyze graph, and I want my bounded area, and you bring it right over there, and you want that point to that point, and my bounded area is going, come on. My bounded area should be 4.251, should be what my bounded area is going to end up being, okay? And if you forgot about the bounded area function, well, then you're going to have to go into your calculator part, which means I'm going to add a page, I'm going to add a calculator. And if that happened, you could menu 43 it, and you could say, before I did that, I could say 2 times this integral over here, which is going to go from 0 to, what was my upper limit, 1.895 tab. And the way I entered these into my calculator, my upper function is f of x, my lower function is f1 of x, my lower is f2 of x. So if I came here and I used my function form and I said f1 of x minus f2 of x tab dx, and when I hit enter, oh, I didn't do that. I want to come up here and then I want to approximate it. I get 4.251. And notice, even if I rounded my limit to 3 decimal places, it's giving me an accurate placement of that, or an accurate representation of that area to 3 decimal places, because that's just the way they're going to set their tolerances on problems like that, okay? Next thing we're going to move right along to is the next page. Well, now we're going to find the total area between these 2 curves. Well, what I'm going to do is I'm going to cheat here, and I'm going to type this into my calculator. Why don't you do the same thing? And I'm going to come back here, and I'm just going to make a whole new graph, and I will be right back. Okay, so I'm back, and what I did was obviously I dialed my windows a little bit closer so I can see the area bounded. But now when you see this bounded area, okay, you're going to see I have bounded area here, And I also have this little niblet of bounded area here. And what you notice is the upper function changes. Okay, so the top function changes. So when I'm setting up an integral, that's going to be important for me to identify, especially if I'm not finding the area with my calculator and I have to find it longhand, okay? And the next thing I need to know is, obviously, I need to know these points, these limits of integration, so I need to know these three intersection points. So the easiest way to do that is just to say menu, geometry, points and lines, intersection points of the red and the blue, and it's just going to chunk those intersections in there for me. And then I'm going to put this one up here because I know it's on top, and I'm going to put this one over here because I know it's on the bottom. And then I'm going to quickly capture this page so that I can place it in my notebook back here. And I'm going to paste that little bugger. And what I'm going to do is I'm going to come right here, okay? And as I'm doing this, notice, okay, again, we want all this green area, and because my top curve changed, what I'm going to do is, because it's upper minus lower, if I did my integral, okay, if I did my integral from negative 3.507, should be what it is there, negative 3.507, and if I did that all the way over here to 1.285 of my integral in here, like my top curve, which is going to be x cubed plus 2x squared minus 3x plus 1 minus my lower curve of 2x, and I went like this with a dx. If I did it that way, notice over here, the top curve flips, and because the top curve flips, now I'm taking my bottom minus my top. That's going to make my heights negative in here, and that's going to reflect this little green area as a negative area. So to compensate for that, what I'm going to do is hopefully, I'm going to try to get this whole thing here. I'm going to take this whole integral over here, okay? And what I'm going to do is, I'm not going to put, oh boy, I got a little nutty with that one, is I'm going to take this top integral and I'm going to integrate from here to here, which is going to be negative 3.507 to 0.222, because remember, I got a round, I'm looking at that 8, and then I'm going to add my integral from 0.222 to 1.285, and now notice my top curve and bottom curve flips. So now this one's going to be 2x minus this other one of x cubed plus 2x squared minus 3x plus 1 dx. And I could type that into my calculator. That's one way to go. Okay. Another way to go is, yes, you guessed it. Actually, I'll put this one up here. The easiest way to go would be do my integral, and hopefully you're yelling at the screen saying, why don't you go from negative 3.507 to 1.285 and just do the absolute value of x cubed plus 2x squared minus 3x plus 1 minus 2x, I think that was my other one, absolute value dx. Yep, you could do that as well, because that's going to make sure all the bounded area is possible. So if you showed your integral setup, that would be an appropriate integral setup. This would also be an appropriate integral setup, and they're looking for the setup in the answer. Well, to be honest, if we're using this CAS calculator, I probably wouldn't want to go to my calculator and do it, but I could. But I'm just going to come here and I'm going to grab this, and if I did my bounded area again, watch what's going to happen. I'm going to go Menu, Analyze Graph, Bounded Area, and I want to go from this point all the way to this point. and it's going to say it's 26.153. Okay. Now, also, if I left my f of x, my f of 2 is top, f of 2 is top, f of 1 is bottom, and if I came through and I added my calculator page and I said that and I went menu 43 and I did my lower limit of negative 3.507 and I went up to 1.285, and inside that I did the absolute value of, and then I typed in my x cubed, I need another parenthesis there, I think, because I want this one to be in one function, plus 2x squared minus 3x plus 1, and then I'm closing that parenthesis and I'm saying minus 2x, close it, and then I'm saying tab a dx. I should get my 26.153 the same way I did before, which I do. And I could also go back and I could type in this whole big string right here for this, the one in the blue box, and get the exact same answer. But they just want to, the biggest thing is find your integral setup and then 26.153, and then you're going to write that out. But if you didn't use absolute values back there, okay, really important to see what's going to happen is, I'm going to screw that up. I'm going to see if I can do this. I don't know if I can. I'm going to come up, I'm going to copy that. And what I want to do, I can do it on my computer relatively quickly here. I'm going to copy that, and then I'm going to come back and I'm going to delete that, and then I'm going to repaste that in there. And if I did not use absolute values, it's going to give me that negative section, and it's not going to give me the total area. It's going to give me like displacement if I, take that negative spot off. So that's what we're going to do there. Now we're going to move here. We have a new one, and I believe this one's going to be given to us at the same time. And if I had this one, okay, this picture is shown, so Kruger needs to get his picture on here. So let me hit pause. I'm going to make a nice picture with my calculator, and I'm going to. Okay, so what I did here was is I drew everything in there, and I have my f of x equals square root of x, and I have my y equals x minus 2. But it's also bounded below by the x-axis, it says. So my bounded area is actually going to be right in here. This is my bounded area, okay, because they needed 3 curves to bound this area. And if I'm finding this, okay, notice when I'm drawing my triangles in here, or my rectangles in here, and I'm coming along, notice my upper curve always stays the same, but notice my bottom curve changes, okay? Well, if my bottom curve changes, well, that kind of means I need 2 integrals. And I guess I need this point 0, 0. That's kind of obvious. But if I did that, okay, notice this is my y equals 0 curve for that pink one. Well, if I did that, I'm going to need 2 integrals because that bottom curve changed where my height is being calculated from. So my area is actually going to equal the integral from 0 to 2. Okay, so what I need to do is I need to bound this area. I'm finding this area first, so I'm going from 0 to 2. And what I'm doing in there is I'm going from my top curve, which is the square root of x, minus the bottom curve, which is x minus 2 dx, okay? So that's going to give me that red area, but now that bottom curve changes, so now I got to add in this area because now my bottom curve is different. So now I'm going to add my integral from 2 to 4 because now I'm going from this point up here to this point, and it's going to go 2 to 4. Now my top curve, it's still the square root of x minus my bottom curve. Oh, Kruger, you screwed up that first one, didn't you? Everybody's screaming, and they're saying, whoa, what are you doing, Kruger? Your lower curve is not what you just said it was. My lower curve here is y equals 0, so it's minus 0 dx. I'm sorry. And then we're going to add this other integral from 2 to 4, and that's going to go from the square root of x minus. Now my bottom curve is at x minus 2 dx, okay? And it's going to find it for me that way, okay? And as I did that, this is a lesson. This is more of an exercise right now, okay? You need to be able to set this integral up. And after you set this integral up, really, it's not too much of rocket science here, because then I can come to my calculator and I don't know, will this bound it or not? I don't know if it will. Menu, I don't think it will. If I went analyze graph, bounded area from there to there. Ooh, see, now it's not. And then I'd have to subtract that triangle out. So my calculator is not going to work for me that way unless I can graph, maybe, I don't even know if this would work. Let me try a 0 in there, get an F3 in there, and now can I find a bounded area? I don't even know if I can do this. Bounded area from this graph and this graph. So from here, now, see, I'm going to have to break this one up. My calculator is going to have a hard time because I got 3 functions. So now that I got f of x, or my upper limit is defined as f1, my lower is f2. What I can do is I can add myself a page. I can add a calculator. I can give it a menu 43, and I can go from 0 to 2. And I'm going to take my f1 of x minus 0, and I'm going to do a dx, okay? And I'm going to say, I got to arrow out of that, and then say plus another menu 43, I hope, from 2 to 4 of now I'm going to be taking my square root of x, and I'm going to subtract x minus 2. Oh, why am I doing that? I'm not doing that. I'm taking my f1, it's easier, of x minus f2 of x, tab dx, and I hope when I hit control approximate, I get 10/3, and that is correct. That or I get 10/3, all right? So that's one way to do that, and it's going to give me my 10/3. So this is going to equal 10/3, which is 3.3 repeating, or 3.333 for the decimal freaks, okay? So that's the way to do it. However, I can change the orientation of this problem, which we will do here shortly. I can change the orientation of this problem, and I can make it so all my rectangles are the same, and I can orientate horizontal rectangles, all right? And that's what we're going to do here in a second. So when we're integrating with respect to y, when we went with dx, okay, what we've been doing is we said integrating with respect to dx, well, I had vertical rectangles where this was my y value, okay? That's bad. And my width is my dx. So my height was y value, my width was a dx, okay? And that gave me, and just remember up here, we were just taking ordered pairs. Okay, top, we're taking x2 minus y2. And this bottom one would be a x1 minus y1. And we were finding this y value was really y2 minus y1 to get this height, find that overall height. And my dx, I don't know why I said minus, those are parentheses there, or commas. And then to find my width, I just took the difference in my x's, but I let my dx take care of that. And when we threw an infinite number in there, we went from a to b of basically y2 minus y1. And remember, the y2, that was my top curve, minus my y1 was my bottom curve, okay? And my width is a dx, okay? Now, because this is a dx, these guys are values of x for your limits of integration, okay? Well, if I spin this the other way a little bit, okay, which we're going to do, and if I spin this the other way and I want to integrate with respect to dy, okay, that all that's doing is that's now laying a horizontal rectangle where the thickness or the width of my rectangle is dy, and my height or width, that's going to be an x value, okay? Because either way, if I said here, this is my x2, y2, and this point over here, that's my x1, y1, well, I can find the thickness by subtracting the y's. And how do I find the height? Well, I'm going to be taking my y2 minus my y1 to get that value, right? Because remember, I'm going horizontal, and I always want to take big or greater value minus lesser value. So what's going to happen is this is going to be the integral, and I'm not going to say a to b. I want to change these variables just because I have it on here, and I'm going to say c to d, and it's going to be from y2 minus y1, which those are, come on, Kruger. We just said we got to go in terms of, so what I'm really doing here is I'm going x's, okay? So it's, I don't know, I got this all jacked up. But these, because this is really a function of y, this is, don't get curled up on these y's. That's going to be my height in terms of x, because these are my functions. The same thing I'm twisting my brain on over here, saying, okay, well, when I take an x2 minus an x1, these are functions in terms of y dy, which means these variables in here are in terms of y, and it's still right curve because it's greater minus left curve, okay? Or if you don't like right minus left, it's greater minus lesser. Same way. And also important, because we're dy, these are values of y for integrating that, okay? And that's where we're going to go. So what we're going to do is we are going to do that same problem again, I hope. And let's see if I still have it in here. Can I just paste that dog in there? I cannot. What the, oh, crap, I can't. So I got to go back. I'm going to delete that out. Get out of there. I hit pause, I'm going to paste it. Okay, so I'm back here. I got this same picture plugged back in there, okay? And it's the same one we did before, but now, because if I integrate, I don't even really want to say horizontally, but if I lay my rectangles horizontally, notice the right curve and the left curve, to find these heights, it's between the same two curves. And if that, what I'm seeing that, see, I'm seeing my width or my height or my thickness of each one of these are a dy. And because they're a dy, that means I'm going to want an integral in terms of y, okay? Which means my limits of integration need to be in terms of y. And if I look at that, I'm going from 0 for y, and I'm coming all the way up here to 2. So if I integrate from 0 to 2, okay, and now the next thing I need to actually do here is I need my functions in terms of y. So if I look at this blue one, I'm really looking at y equals the square root of x. I need to solve this equation for x, so I have y's in here for my, but that's my left one. So this one is going to be, if I square it, I'm going to get y squared equals x, okay, because that's a half a parabola there. And if I took my other one, y equals x minus 2, and I solve that for x, I get y plus 2 equals x, right? So this is really that red curve, and this, in terms of the other variable, is that curve. It's because if I'm integrating horizontally with respect to y, my function inside of here needs to be variables of y only. So now I'm thinking of the height. I'm taking my greater minus my lesser to find this height, which is right curve, which that right curve is y plus 2. So I'm taking y plus 2 minus my lesser curve, which is a y squared, dy. And that's my height and width. And what we're going to do is we're just going to come back here to our calculator quick. And we know this better equal 10/3 because that's what we got before. And it better equal the same thing. So now I'm going to come back here and I'm going to add myself a new calculator page just so it's clean. I'm going to say menu 43. And I'm going to integrate from 0 to 2. And inside here, I'm going to give it my y, because we're going y plus 2, parenthesis, minus, here's a y squared when I solved it, and that's a tab, that's a dy. And when I hit this bugger, 3.33, or 10/3, it works out. So just know when you're going horizontally, when your heights are moving horizontally, okay, your function needs to be in terms of y. And when your function, and I should say when your things are going vertically, when I'm going vertically, my function needs to be in terms of x, which I can't really show you there. But so type it in. Horizontal integration is in terms of y. Vertical integration, if I can say it like that, is in terms of x. If my rectangles are sideways, like that, I can see they are that thick. They are dy thick because they're slicing the y-axis. If my rectangles are vertical, I can see their thickness are dx. Therefore, I need a dx. I need my function in terms of x. Okay. Now I can get an area with one integrand if I spin the orientation of that problem. Hopefully that makes sense. That's where I'm going to stop today. We're going to do a couple more on Monday, and then we're also probably going to have that formative on Monday. So have a good rest of your day, and also have a good weekend.